Imagine standing inside a building that is taller than 100 floors. Suddenly, the ground begins to shake, the walls vibrate, the windows rattle, the entire skyscraper starts moving not by a few millimeters, but by several feet. It sounds terrifying, but here's the surprising part: this movement is completely normal. In fact, if a skyscraper did not move, it would be far more dangerous. Every year, thousands of earthquakes strike around the world. Some are too small to notice, others can destroy entire cities, yet many of the world's tallest buildings remain standing. How can a building made from thousands of tons of steel and concrete survive the incredible force of an earthquake? Why doesn't it simply collapse? The answer is hidden inside one of the greatest engineering achievements ever created. Modern skyscrapers are not designed to resist earthquakes, they are designed to move with them today. Going inside these engineering giants to discover how skyscrapers survive earthquakes and why the tallest buildings on Earth are actually built to bend. Before we understand how skyscrapers survive, we first need to understand what an earthquake really is. The ground may look perfectly solid, but deep below the Earth's surface, massive pieces of rock, called tectonic plates, are constantly moving. Most of the time, they move very slowly, only a few centimeters each year, but sometimes these giant plates become stuck. Pressure builds up for years, sometimes for decades, then suddenly that pressure is released in just a few seconds. The result is an earthquake. Powerful waves travel through the ground in every direction. When these waves reach a building, they push it back and forth again and again. A small house can crack bridges, can shake violently, and tall buildings experience enormous forces. The taller the building, the greater the movement near the top. Without special engineering, that movement could become catastrophic. So engineers faced a difficult challenge. How do you build a structure hundreds of meters tall that can survive when the ground beneath it won't stop moving? The solution was not to make buildings more rigid, it was to make them smarter. At first, it sounds strange. Wouldn't a stronger building be a safer building? Surprisingly, the answer is no. Imagine taking a dry stick and bending it, it snaps almost instantly. Now imagine a flexible branch, it bends, moves, then returns to its original shape. Modern skyscrapers follow the same principle. Instead of fighting the earthquake, they move with it. Engineers carefully design the steel frame to be flexible, not weak. Flexible as earthquake waves push the building, the entire structure can sway from side to side. Sometimes the top of a skyscraper moves more than 2 meters, even though people inside may only feel a gentle motion. This controlled movement reduces the enormous forces that would otherwise break columns, crack concrete, or collapse entire floors. Special steel connections act like giant joints. They absorb part of the earthquake's energy instead of allowing that energy to destroy the building. Every beam, every column, every connection works together, spreading the force across the entire structure instead of concentrating it in one place. This is why modern skyscrapers don't try to stop earthquakes, they simply ride them. Just like a tree survives a storm by bending instead of breaking. But flexibility alone is not enough. Some earthquakes are simply too powerful, so engineers added another layer of protection. Hidden deep inside many modern skyscrapers are incredible systems that most people never see. One of them is called base isolation. Instead of attaching the building directly to the ground, engineers place special giant bearings between the foundation and the structure. When the ground shakes, these bearings move first. The building above moves much less. It's almost like the skyscraper is floating on giant cushions. But that's only the beginning. Inside some of the world's tallest buildings, there is another amazing invention. It's called a tuned mass damper. Imagine a giant metal ball weighing hundreds or even thousands of tons suspended near the top of the building. When the skyscraper begins to sway, the giant mass moves in the opposite direction. This motion cancels out much of the vibration, reducing the building's movement and making people inside feel much safer. Without this technology, the swaying could become far more violent. These hidden systems work silently 24 hours a day. Most people never even know they exist, yet during an earthquake, they become one of the most important reasons a skyscraper remains standing. This technology isn't just a laboratory experiment, it protects some of the most famous buildings on Earth. Take Taipei 101 for many years. It was the tallest building in the world. One experiences powerful earthquakes almost every year, yet Taipei 101 was designed for exactly that challenge. Near the top of the tower, engineers installed a gigantic golden steel sphere. It weighs more than 600 tons. When strong winds or earthquakes push the building, the massive sphere moves in the opposite direction, reducing the movement of the entire tower. Visitors can even see this giant damper inside the building. It's one of the few engineering systems normally hidden that has become a tourist attraction. Now think about the Burj Khalifa, the tallest building on Earth. Although Dubai rarely experiences major earthquakes, its engineers still designed the structure to handle powerful vibrations. Its unique shape breaks up strong winds. Its reinforced concrete core provides incredible strength, and its flexible design allows the tower to move safely without suffering damage. These skyscrapers may look completely rigid, but in reality they are constantly moving, adjusting, and absorbing energy. It's this invisible movement that keeps them standing when nature shows its true power. As cities continue to grow taller, engineers are already designing the next generation of skyscrapers, buildings that don't just survive earthquakes, but actively respond to them. New smart sensors are placed throughout the structure. The moment an earthquake begins, thousands of sensors measure movement in real time. They instantly send data to powerful computers inside the building. Within seconds, the system knows exactly where the greatest stress is occurring. Some future skyscrapers may even use artificial intelligence to adjust their safety systems during an earthquake. Engineers are also developing new materials, special concrete that can repair tiny cracks on its own, high-strength steel that bends farther without breaking, and advanced dampers that react faster than ever before. The goal is simple: to build skyscrapers that become safer, smarter, and stronger with every new generation. The buildings of tomorrow won't just reach higher into the sky, they'll also be better prepared for whatever nature throws at them. What once seemed impossible is quickly becoming the new standard in modern engineering. So, how do skyscrapers survive earthquakes? The answer is not because they are the strongest buildings, it's because they are among the smartest. Every beam, every steel column, every foundation, every damper, and every hidden safety system has one purpose: to absorb energy instead of resisting it, to bend instead of breaking, to protect the thousands of people inside. The next time you look up at a giant skyscraper, remember this: what you're seeing is much more than steel and concrete. You're looking at decades of scientific research, millions of engineering calculations, thousands of safety tests, and one incredible goal: keeping people safe even when the Earth itself won't stop moving. Modern skyscrapers are not built to fight earthquakes, they are built to dance with them, and that is one of the greatest achievements of modern engineering. If you enjoyed this documentary, don't forget to like, share, and subscribe to RailForge ***, because here we uncover the incredible engineering behind the world's tallest buildings, mega structures, and the technologies that shape our future. Thanks for watching, and we'll see you in the next documentary.